and the journey of green hydrogen in this entire chain. And the first question that we have to ask is why hydrogen? This is especially for those who are looking at hydrogen as a kind of a new venture, especially with the whole world talking about it. So there is this tendency of saying that we also need to get in, kind of a thing. Now, hydrogen is having the highest energy amongst all the various fuels. And in my opinion, which I have often said in seminars and other meetings, is that the biggest reason why somebody has hydrogen is that it becomes a energy security for a country, because today any of the other energy options that you look at, which would be diesel, petrol, natural gas, or whatever, you end up having to depend upon some country or the other which may have these natural resources for whatever reason. Whereas with hydrogen, since you would be able to convert it from water and technically even from seawater, so you have the option of, without being dependent on somebody outside, have a certain level of energy security for a country. And as far as hydrogen is concerned, for various reasons, it has been classified in different colors. Now, while people talk about green hydrogen, which is essentially hydrogen generated through electrolysis using renewable electricity, then you have something like pink hydrogen, which is using nuclear energy. So different countries have different kinds of definitions that they adopt. But as far as we are concerned for this presentation, the color is irrelevant in a manner of speaking, because the behavior, the performance, and the properties of the gas do not change by way of its definition of any particular color. And as I said earlier, this presentation is for everyone, right from students to people who are leading projects. To give a very slight historical background and key info about this, hydrogen is not something that is new. It's been there since the 17th century. So we are literally talking about more than 4 centuries since its knowledge and usage in the industry for various scientific activities. It exists in abundance, as I said. Uh, the key is that it requires power to produce, which means one needs to look at an energy versus power balance for this. And compared to very other definitions, one key definition which especially the Americans have followed is that whether there's any carbon produced in the process of producing hydrogen. And I think India is also probably including that as a part of the definition. So which means that it is not just solar or wind or hydropower that comes in as a renewable energy, but nuclear also can be an input source which can change the entire, let's say, dynamics of this particular industry. Safety is a very key important factor, especially when handling this. And above all, one needs to understand that hydrogen is an industry that is happening simultaneously across the globe. Whether it is a smaller country or it's a large developed country, both of them are talking of hydrogen at the same time. Unlike earlier, where one would wait, like India would wait for a while before something is, proved and understood in, let's say, US and Europe and such places. So India would have the benefit of the learning from others. But this time, including India, everyone is talking of hydrogen at the same time. So as I was mentioning earlier, when you look at the energy content and when you look at diesel, which is somewhere around 45.3, you have hydrogen at 142, which is almost 3 times that of diesel in terms of the energy that it gives you. But on the other hand, when you look at the density, which is what is important for storage, you will find that the graph is exactly a mirror image where you can store diesel in very large quantities in a given space, whereas hydrogen is hardly 5% or less than 5% of what diesel could do for you. So which means that you have a very wide bandwidth of what the gas can do. And that is where the first contrarian behavior of hydrogen and its challenges start. Uh, After a long time, I sort of debated and then I decided I would jump to something which I wanted to have it in the end. And I will tell you the reason why. Now, when you look at the various standards in India, or for that matter in the world, where it is an extremely important factor when you're doing anything in the hydrogen sphere, what you find is that globally these standards evolving, they are changing and they're improving. So as a consequence of that, what happens is, along with stuff like periodic retesting and other certifications and so on, there are various other minor points which add to the complexity and cost of what, let's say, a nation outside of the US and Europe ends up doing in hydrogen. And one of the factors for that is, for example, when you take the mobility application, which means like whether it's on a train or a bus or a truck or a car, whatever, you have different standards, and the design factor of these are between 2.25 to 2.5, or rather actually 2.4 to be more precise. But when it comes to storage and transportation, apart from the fact that in some standards you have between 2.25 to 2.5, there are others where the design factor is 3. Now, India has already come up with a few standards. Apart from the existing ones, there are some new standards which have been created for the hydrogen industry, especially for the mobility sector. And how these standards affect our whole subject, I'll come to that in a minute. Now let's look at the way the industry is working currently. When you look at the mobility sector, again, meaning the transportation in terms of whether it's a train or a bus or truck or whatever, normally they use either a 350 bar or a 700 bar storage tank currently. And these tanks are designed with a design safety factor of between 2.25 to 2.4. When it comes to storage and transportation, uh, these vary from as low as 200 bar right up to 950 bar. And the design safety factors vary between 2.25 to 2 up to 3. So where do these things make a difference? One, suppose one were to be looking at a composite cylinder, for example, and I'll come to composite cylinders in a minute, and you're using carbon fiber, then a safety factor of as low as 2.36 is allowed. Whereas you can also make the same cylinder using glass fiber, where the requirement of safety is 3. Now, what exactly does it mean? It means that if you are having an operating pressure of 250 bar, then your design pressure would be either 590 bar or 750 bar, depending upon what is the safety factor that you need to follow based upon the standards that you take. Now, as I was mentioning in the previous slide, there are certain standards which demand a safety factor of 3, where even for a carbon fiber, they make it mandatory to have a safety factor of 3. So next, if you take, let's say, an operating pressure of 350, you need to go up as much as 1050 bar. And if it's a 500 bar cylinder, you need to design it for actually 1500 bar. So when you look at these kind of pressures, when you look at a safety factor between, let's say, 2.36 and 2.5, designing a cylinder or a vessel between, let's say, 1180 bar and 1500 bar is a pretty significant jump, and it has a whole host of, uh, let's say, implications across the entire chain. Now, as I said, there are different standards available in the market today, which people have been following. There are some new standards that have come in, which have been introduced recently, like for example, the EN17339. Since we are talking about storage and transportation, I will stick to that because that makes a very important factor in the whole presentation. The current standard that has been in, let's say, vogue from a long time is, for example, an ISO 11119 or a EN 12245, where the design factor required is 3. Whereas on the other hand, the latest standard, which is EN 17339, allows a safety factor of 2.36. So what happens? Suppose, let us say you have an existing cylinder of 250 bar operating pressure, which was designed to a 11119 certification. Then the same exact cylinder, without you doing absolutely anything, you can now say that it can operate at a pressure of 317 bar in the field. A 300 bar would become 381. Similarly, a 500 bar could become a 635 bar operating pressure, which means you have a significant increase in its storage capacity, and also the fact that a customer can now, because he can store more, it becomes an attractive option to him. But then what is the implication of this across the global supply chain, as I would call it? Now, you had a tank that was there from the last 10 years, which had a safety factor of 3. Now, the same cylinder can be used with a safety factor of 2.36. So what happens? While the tank, there has been no change whatsoever, you suddenly have the valve, the thermal and the pressure relief devices, the other parts that go along with it, like a regulator or whatever it is, all of them have to now operate at, let's say, 635 bar instead of 500 bar. Or if you take 350 at 445 bar instead of 350 bar. Now, people may or may not have such products, or even if they have a product, it may not be tested. It may not have the certification. So you have challenges there. Next, you come to pipes and fittings, the same thing. And then you're talking about the infrastructure like the dispenser and everything. Now, if you have a tank which is already suited for 500 bar, and now you're allowed to fill at 635, you may not have the infrastructure in the dispenser to fill it at 635. And then you have the next challenge of the overall system design and safety, because when you design the rest of the system, like all the pipings and whatever else you did in a plant, that may not have been designed for 635 bar instead of 500. And then none of these may be tested also in terms of its performance. So consequently, what happens is, even though a new standard came in, which should have actually reduced cost for a lot of people, in reality, what happened was that the cost went up because the other 5 items that I'm talking about were just not there. So these are the kind of challenges that we are facing in the case of hydrogen. So now, when you look at applications, uh, as I mentioned earlier, these are some of the broad applications that you have, where if you take a Toyota Mirai car, it operated 700 bar with 3 cylinders. You have buses and trucks which run at 350 or 700, train. And then when you need to transport hydrogen, you can have a hydrogen train, as you could see at the bottom left-hand side, the bottom left-hand side. And when you look at the inside of it, uh, what you see on the right side is how you would look at it. So now let's look at the hydrogen delivery chain, what exactly happens. So you have an electrolyzer where hydrogen is produced at maybe around less than 30 bar. Then you have a compressor which will compress it to either maybe 200 or 350 or 500, or it could be a liquid hydrogen. So you store it because you need to store the hydrogen that you produce. And then, assuming that you're using the hydrogen in the same location, you would again reduce the pressure back and use it either in a fuel cell or in a process where again the pressure requirement is less than around 20 bar normally. Now, suppose you decide to do the transportation of the gas from the production site to a consumption site, you would be compressing it to, as I said, around 250 or 500 bar, taking it in a truck, and at the location where you're going to use it, again, reduce the pressure and then use it. On the other hand, you could have a situation where you need to fill it up into a truck or a bus, which means that because the pressure reduces, you need to again compress it, take it into a dispenser, and then dispense it into a truck or a bus. Now, what is the implication of this? Is the energy chain. Uh, in the energy chain, what happens is you have energy to produce hydrogen, then you use energy to compress the hydrogen, then you need energy to maintain that storage, depending upon whatever storage you're going to use, and then you're going to use that energy in the process. On the other hand, after compression, you might again expend energy to transport the hydrogen, and then at the delivery location, you will have energy to maintain the storage, and then you will need energy to dispense the hydrogen, which could be used either in automobiles or in a process. And then if you are delivering it to a vehicle, what happens is that the pressure reduces, which means you again need hydrogen to compress the hydrogen and take it back. So which means that the entire chain uses a significant amount of energy. And the lesson from this is that it is important to map the energy chain across the whole chain so that you can balance the energy and not have a situation where you are spending more energy, but actually, let's say, generating or utilizing it or having lesser benefits from it. So if, let's say, you are having a nuclear power plant as the input power, then you could even have situations where the heat generated can be used to produce hydrogen. So now let's come to the storage options. You have stuff like salt caverns, and I'll go each of them one by one. Cryogenic storage, which is a proven technology. High pressure composite tanks, which is again a proven technology. Cryocompressed storage, which, as the name signifies, is a combination of cryogenics and high pressure. It has been demonstrated and under commercial development right now as we speak. Then you have metal hydride storage, which is a story that is still being written. And then, of course, you have pipelines. These would probably take time. Maybe the existing infrastructure can be a solution after a rigorous due diligence technically, but still. So let's come to salt caverns. Salt caverns are essentially an artificial cavity created in a geological salt deposit, which is deep underground. So you drill into that location, you pump in water to dissolve the salt that you have located deep underground, remove that, and then you create space as you can see in these photographs. And then you push in hydrogen into these caverns so that the hydrogen is stored here in large quantities, and it can be as much as around 200 bar because you have dug deep into the ground and you automatically have that, let's say, the pressure containment that happens. These have normally been used where there is an existing pipeline and where they want to have a fallback in an emergency when they need to, let's say, repair the pipeline or some such reason. So this is where it is being used. And then while these are safe and long lasting, in the entire world right now, there are just about 4 such locations. So availability of such a location is important for you to be able to even use this kind of a solution. Now let's come to cryogenic storage. This is again proven technology, as I said, where the hydrogen is stored in the liquid form. This technology is already being used globally in quite a few places. Now, when you look at the different gases which we are currently using in the field in a liquid form, you have natural gas, which is at about minus 161 degrees centigrade. nitrogen at minus 196, and hydrogen is actually at minus 253. So you can imagine the level of uh, you know cryogenic temperature that you need to reach to be able to convert it into higher liquid and then store it by maintaining it at a certain temperature. So today, when you look at LNG, globally, you do not see it very popularly in terms of commercial applications like on a truck or a bus, even though there are a large number of them in the road. But when you compare it to, let's say, CNG, which is the compressed natural gas form, these are probably hardly a few percentage compared to the compressed natural gas form. Whereas LNG is essentially used for bulk shipping to take LNG from, let us say, the Gulf to the US, or maybe somewhere in the Gulf to India, or something like that. Now, the kind of energy required to liquefy is anywhere between 12 to 15 kilowatt hours per kg. So what happens is that the total energy for liquefaction and to maintain it is pretty high, which means that the economies of scale required to go in for such a project is very high. Globally, from what I've managed to understand from people, the current storage is around 5 to 10 tons per day is the kind of capability that's available around the world. Now, the other place where you would have heard about cryogenic liquid hydrogen, but without the word hydrogen being used, is the cryogenic rocket engine, which is what you would have read every time you talk about ISRO having launched a satellite, every time ISRO uses the GSLV rocket. These are all cryogenic rockets where hydrogen is stored at minus 253 degrees centigrade. They are mixed with oxygen, and then you get an extremely high thrust, which something that no other fuel which is available and known to man can provide, which is the reason why they use this. Now, this entire system is extremely complex, and the thermal and structural challenges for you to be able to store it at that kind of temperature is very high. So the safety factor and the safety systems and culture that is required is again very significantly high compared to any other gas and any other normal systems that we today follow. Very interestingly, this particular technology is not only proven, but it is even manufactured in India. But yet, very few people or nobody really uses it because of the complexity, the cost, and like I said, the scale required. For example, someone like NASA has a tank of about 5,000 cubic meters. Uh, Now, they are talking of going up to 20,000 and 40,000, but do they have it as yet? No, they don't. So what happens here is that this particular technology is predominantly used in the aerospace and defense segment. So when you start looking at it at a commercial level, it has a whole host of challenges, which I will come to towards the end of my presentation. And today, the preferred design for liquid hydrogen storage is a spherical design rather than a cylindrical one. And the picture at the bottom right, what you see is a liquid hydrogen tank manufactured in India and exported to Korea. Now, the third kind of storage is metal hydride. Essentially, here what happens is there are certain metals and alloys which are capable of reversibly absorbing and releasing the hydrogen. So when you, let us say, want to store hydrogen, there is heat released and it absorbs the hydrogen into itself. And then when you want to use the hydrogen, there is heat that is absorbed and then the hydrogen is released for you to use the hydrogen as a gas. Uh, there are materials like lithium hydride and sodium borohydride and so on, which have been used. But then the IP is in these kind of material and the way the systems are designed. The biggest advantage here is that you can get significantly high storage efficiency at a very low pressure. Now, this technology is yet to go commercial. It is still at a lab level application, as what I would call. We really do not have information about the costs and the supply chain issues. And the entire system has a number of unstable, let us say, challenges, because of which the US, for example, which is probably, I would say, the benchmark in the world for safety systems, has suggested many safety safeguards for its usage. But does this storage system sound exciting? The answer is yes. So if you want to get an idea of why is this okay. So when you look at, for example, in a car, if you were wanting to be using metal hydride or hydride kind of a storage, the size of a tank would be somewhere, depending upon the material that you're using, would be like what you see in the first and the second ones here. If you were to be using liquid hydrogen in the same car, this is the third one. But if you were to be using hydrogen as a compressed gas and as much as a 200 bar, as low as 200 bar, this is how large the tank would be compared to the size of a car. But yet, 100% of the cars in the world today use compressed hydrogen gas and not any other form of hydrogen. Now, the next technology, which is, like I said, has been demonstrated, but expected to be commercially available by 2025, hopefully, is a hybrid technology where cryogenic temperatures and high pressures are combined, where the gas is cooled and stored at 400 bar pressure. Again, composite cylinders are used, but then these composite cylinders are designed to be able to handle cryogenic temperatures. Now, the technology, as it is claimed by way of the demonstration, is that it can have a 40% higher amount of volume as compared to a 700 bar system available in the world today. And the station cost, which means a dispensing station where you would probably refill your truck or bus with hydrogen, the cost of that is supposed to be 25% of setting up a 700 bar system in terms of a total cost of ownership. Now, when you look at what this can do, a truck can have something like 100 kgs of hydrogen storage with one of these kind of systems that you see. The one on the top right hand with 4 tanks will probably have 25 kgs each, and 4 tanks would give you about 100 kgs. The one on the left top will give you around 50 kgs, and the one on the bottom, which would be for you to transport hydrogen from point A to point B, could carry as much as 2,500 kgs of hydrogen. Today, when you look at a truck, you are not able to carry more than around 30 kgs, 33 kgs of hydrogen at 350 bar, and maybe around 50, 52, 55 kgs of hydrogen at 700 bar. And when you look at the bulk transportation, even at 500 bar, you are not able to carry more than around 1.1 tons of hydrogen today. So the storage solution today, that is what I would call as 99% across the world that is used, is high pressure storage using composites. So I'm going to be spending a lot more time on talking about this particular kind of storage. Now, there are different kinds of cylinders available in the world today, which are classified as type 1, 2, 3, and 4. Type 1 is essentially what we all of us know, which is a steel cylinder. A type 2 is a intermediate solution and a technology that came in wherein they try to reduce the weight of the steel cylinder, but then nobody in the world really uses it. And the only place where you can possibly even see it is probably China. Otherwise, nobody in the world would touch it. The third is, of course, type 3, which is a carbon composite cylinder, with an aluminum liner, and a type 4, which is again a carbon composite, but with a plastic liner. So I will come to this in a minute now. So when you look at steel cylinders, what are the problems? One, they're extremely heavy. They are the oldest. They very easily corrode and rust. And especially if you're in a coastal area, or let's say a country like Sri Lanka, would which has got a very, very large coastline, and almost every city is adjacent to the sea, you would have these cylinders corroding so quickly that in the Gulf area, for example, I have seen that these cylinders get replaced every 5 years, because that's how quickly it corrodes and becomes, let's say, unsafe for usage. Now, when you talk about hydrogen, you have a significant problem of metal embrittlement, where the hydrogen, as the pressure increases, starts weakening the steel cylinder itself and making it embrittled, like, where it can easily give way and, create a safety problem for you. So today, including in India, nobody uses a steel cylinder for more than around 170 to 200 bar storage pressure. There are special grid states which can be used for up to 500 bar. They have been proven, they are in the market, but they are quite expensive. And at the same time, their track record is yet to be seen. Meaning that if you were to ask one of them who supplies it, they would thump the table and tell you it's a great solution. And I would agree with them. I would not dispute it. But if you ask them, has it been working in the field for about last 5 years, 10 years, 15 years? They would have an hesitancy to give you an answer to that. And because of the fact that these tanks are so heavy, the amount of product that is carried is insignificantly low. So today, as we speak, steel tanks are not an option at all to store hydrogen by anybody, especially in bulk, and especially in the mobility applications on any kind of a vehicle. So the option that people use is composites. Now, with composites, you can actually go up to all the way to 950 bar storage pressure. And once again, this technology has its roots and foundation in the defense and aerospace segment, which uses carbon fiber. So it would be technically possible today that a 250 bar system may be more cost effective than a 500 bar system. And when you start looking at the system cost, as I was mentioning earlier, the compressor and the composite tank, when you're talking of a 500 bar, you could have the compressor almost 3 times more expensive than a 250 bar, and a 500 bar would be more than 2 times expensive as a 250 bar system. So we need to, as I mentioned right in the beginning, find out the optimum cost by factoring in the cost of compression and do a system cost analysis. And as I said earlier, again in the beginning, the generation and usage application of hydrogen, when it is less than 30 bar in a particular location, it is an absolute waste of energy to pressurize it to 350 or 500 and then again depressurize it to 30 bar, especially if it's in the same place. So, as I mentioned earlier, if it is at the same location, as we speak today, a 250 bar or 200 bar storage could be probably more cost effective than any other solution. So how does a composite tank look? A type 3 or a type 4, as it is called, is the preferred choice for hydrogen storage applications, as also even for CNG for that matter. A type 3 composite tank has an inner layer of aluminium, while a type 4 composite tank has an inner layer of plastic. Up to 350 bar operating pressure, whether it is a type 3 or a type 4, globally it does not matter. Both are equally good and acceptable, and nobody would get into a debate between type 3 and type 4 when you're using it up to 350 bar operating pressure. A a user must then focus only on the price, delivery, service, whether a particular size tank is available to suit their application, and that has to be the focus. Now, when you start going beyond 350 bar and you start hitting 700 bar, especially on board applications, today a Type 4 cylinder is preferred because I think, to the best of my knowledge, a Type 3 is not available beyond around 450 bar. So a Type 4 is essentially preferred when it comes to using it at higher pressures. So I would say that going forward, composites are the only solution for hydrogen, at least in the next 5 to 10 years at the minimum, as I would say. And so, like I said again, do not dilute the argument by getting into which technology. Between Type 3 and Type 4, anything that you are going for would be equally good and acceptable. So how does the structure essentially look? I mean, to give you a very basic understanding. See, you have a plastic or an aluminum liner, and then you have the carbon fiber around it, which is wound around it. And then you would have what one calls as an outer, uh, sacrificial layer or whatever, which would be essentially for giving it certain mechanical strength when you're using it, because you might suddenly drop it or you might accidentally hit it. So for that kind of a thing. And normally when this is being wound, the way it is done is that the carbon fiber is wound in such a way that where your valve is being fixed is completely hermetically sealed, so that there cannot be any leakage in those joints. So the manufacturing process is like this. When you take a Type 4 cylinder, for example, you have a long plastic pipe, which could be, let's say, 6 meters long. You can cut it to whatever length you want. And then you have these white portions that you see on either side, which are injection molded domes, which are then welded to the end of either end of these and creating a cylindrical shape. In the case of aluminium, you would have an aluminium cylinder completely of this shape, since you will be able to form with aluminium this kind of shape. So you have it in aluminium instead of plastic. The only reason why, or rather the main reason why Type 4 came in compared to Type 3 is that, for example, you take this pipe, like I said, which is 6 meters long. Let's say you have a cylinder which is now 3.5 meters long, and somebody tells you that, look, I don't want to change the diameter, but instead of 3.5 meters, can you give me a cylinder that is 3.8 meters long? You just cut the pipe at whatever point you want, making it 3.8, and then do the same welding, and then you have a tank literally within 24 to 48 hours. So the speed of development with a Type 4 tank is very, very high, because of which the Type 4 became fairly popular, especially where larger size tanks were being used. The other option is you can go in for blow molding of the liner, which is essentially used where you're having very large volumes of a particular size of cylinder. After you have this liner ready, you go in for winding. You could have a winding machine, which you can see on the left side, which could have maybe 2 cylinders at a time, 3 cylinders at a time, 5 cylinders at a time, which would then increase your productivity and bring down the cost. And after the cylinder is manufactured, it goes in for heat treatment, other processes in a complete assembly line kind of a facility. And then you have the finished cylinders, which are shipped to customers for usage. So the benefits of a composite storage system is you have a 70% weight reduction compared to steel, which means a 100 kg steel cylinder, the equivalent of that in composite would weigh only 30 kgs. So you have uh, two benefits that come from there. One, you could, on a system, let's say it's a truck or a bus, for example, technically speaking, have 3 cylinders of the same size instead of one for the same weight and still transport or use steel, getting longer range or larger quantity of gas that you would carry, or if you're using even just one, the 70% weight reduction results in, let us say, fuel efficiency, carbon emissions. You have these kind of benefits that come in. There is zero corrosion. In a composite cylinder, there would be no corrosion because of any impurities that might be there in the gas. It has a long fatigue life and a very high impact strength. It is absolutely safe, and it meets standards that are more than that of steel in some of the cases. This has been tested for 30 years life cycle. It is assured for 20 years because that is what currently the statutory regulations allow. And these cylinders have been used at least since 1963 to the best of my knowledge. So which means we are talking of more than 60 years of track record of composite cylinders in the market. And if you want to get an idea of the kind of applications, mission critical applications where it has been used, it's been used on the space shuttle, it's been used in the International Space Station. So these are the kind of applications where it has been used, which will give you an idea of the kind of reliability, safety that these cylinders offer you. The other thing is that today, when you have a steel cylinder, you got to go in for a periodic retesting, hydro testing, all of that. Whereas with a composite cylinder globally, only a visual inspection is recommended. So in general, what happens is your system integrity, cost, risk, all of them reduce and your safety increases. There is absolutely no metal embrittlement because there's no metal. So especially when you talk of type 4, you can go in for very, very large tanks of as large as 8,500 liters water capacity. Now, to just give you a kind of an idea of the next challenge when it comes to hydrogen, including in the terms of storage. Let us talk of, let's say, 3,000 kgs of hydrogen to be stored. And I've taken 3,000 kgs because of a particular customer requirement in India. Now, you could store it at 250 bar, 300 bar, 350, 450, 500. There are different manufacturers who offer different kind of tanks. So I have just done a kind of a dipstick study with different tanks. Now, what happens is the first thing you must understand is a 250 bar. Let us say you're having a fill efficiency of 1, which means that whatever you're storing is at 250 bar pressure. When you go to 300 bar, your pressure ratio increases to 1.2. Your fill efficiency is still at 1.2. But when you hit 350, while your pressure ratio has gone up by 1.4, which means 250 to 350, that increases 1.4. The amount of hydrogen that you can store is only 1.3 times more. With 450, it's 1.6. With 500, when the pressure ratio is doubled, one would normally assume that you should have twice the amount of storage in the same tank. But sorry, you have only 1.7 times, which means that the fill efficiency reduces in the case of hydrogen. So you have a challenge when you're talking of using, let's say, different pressures. And the number of tanks that you would need for this varies from, depending upon one of the larger size of tanks that is there, which is 8,500 liters, which would be just 20 tanks, to around 98 for a 1,666 liter tank, going up all the way to 358 cylinders for about a 350 bar tank. Today, for example, in India, they use a 350 bar tank. So you are essentially having a very large number of tanks when you can have a much, much lesser number of tanks in reality. 3,000 kgs of hydrogen means just about 100 trucks can be filled. So now do the math that depending upon the kind of demand that would be there, what is the kind of storage solutions that one needs to cater to? So if today, for example, India, is talking of 5 million tons of hydrogen. So when you look at one of these larger tanks, you are talking of, I'm now not talking of tanks here, the number of manufacturing plants to manufacture these tanks. You will require more than 20 factories just for catering to this requirement in India. If you decide to go in for one of the smaller sizes, you will require more than 40 factories in order to meet this particular kind of an infrastructure. Now, as we speak today, this can change 1 year from now or 5 years from now. I don't have a crystal ball to predict, but as we speak today, the existing manufacturing facility has a 40% shortage to meet the current demand in the world. So the unpopular opinion, though it is the popular perception, is storage is going to be, in my opinion, the bottleneck globally, but technology and policy can disrupt this. So now let us say we talk about transporting gas. Again, to give you an idea, these are all existing solutions that are operating in the marketplace. You have solutions which can carry 30,000 water liter, 39,900 liters water liter, and so on at different pressures. Now, the amount of gas it carries is given here, which varies between 555 kgs to 1,115 kgs. This is the weight of the container. This is the number of cylinders. So the percentage of the gas that is carried for a given weight of the system that you're transporting is as low as 3.5% and a maximum of 4.1%. So which means that when you transport gas today from any place to any other place, 96% you are carrying dead weight, which has no use whatsoever, and only 4% is the product that is being carried by you. Which is why I recommend that where people are talking about storage and transportation, try seeing that you use the larger size of cylinders. Go in for manifold designs so that you don't have a tank valve in each tank and reduces that cost. Look at a kind of a hydrogen village or cluster concept where you deliver hydrogen only in a small area after producing it in that particular area. And again, as I mentioned earlier, if production and consumption in the same location, going for a lower pressure, at least as of today. If the prices change tomorrow, you can definitely go up to a higher pressure, which makes logical sense. So now, taking the same example, suppose you need to refill 100 trucks per day. You will need between 21 tanks if you use a system like what you see at the bottom right, which are all 40 feet long cylinders and just 4 of them being used. Or you have another one which you see on the top right, where you require just 9 cylinders of a smaller size. So depending on that, you would have anywhere between 21 or 89 going all the way to 381 cylinders to transport, to just fill 100 trucks per day. Okay, and in one such system, as I was mentioning here, the previous, you have anywhere between 3 to 6 numbers of 40 feet containers which have to move on a daily basis between two locations for you to be able to cater to just 100 trucks. So you can now start multiplying the number of trucks or buses that one is planning for, and then see how many other trucks and buses will, trucks and containers have to move to cater to their requirement of fuel. So to sort of sum up, the hydrogen supply logistics, as I would recommend to anybody today, is that if you are producing hydrogen and utilizing it in the same location, look at a sunlight storage of about 200 to 250 bar. And then if you are dispensing it to vehicles, then you can have what I call as a distributed storage between 200 and 500 bar, so that your overall cost reduces and you have only a few cylinders at 500 bar, so that you use it by way of a differential pressure, and then as the pressure reduces, you can keep using other cylinders of a lower capacity, so that your overall storage cost reduces significantly. Now, in the beginning of my presentation, I mentioned that I would be talking to you about some of the challenges. Now, these challenges are, now let's take liquid hydrogen, for example. The entire technology, the sale, everything is driven by the defense and aerospace industry and companies like NASA or ISRO. Now, even an ISRO will not say, I want it cheap, because they cannot afford a 500 crore or a 600 crore rocket and a satellite to not work. So, which means that they drive what is required. Now, very often, as it happens in the defense industry, especially, and more so in, like I said, in the defense segment, technologies then become commercial. So today, there might be a technology that NASA or someone like that is using, or the European Space Union is using, but that technology may not have been allowed by the governments to be given out commercially. So we don't know what I call as what we don't know in this particular factor. We only know what has been offered to us by a supplier who says, I have a technology for liquid hydrogen, and we accept that. Now, there are huge product development costs, which means that while a NASA or ISRO would pay, whatever kind of money that might be required, for a commercial enterprise, that may not be possible. And then you have the cost of complexity, as I call it, because you need to handle this. So this entire technology being driven by the defense and aerospace have all these kind of challenges. Now, these challenges are common even to the case of compressed hydrogen, but because of the fact that compressed high pressure cylinders have been around in the commercial space since at least about, I would say, 1995, around that. So as a consequence of that, the impact of this commercialization, product development, all of this has reduced significantly. But today, the problem that the high pressure hydrogen cylinder market faces is, one, the price of carbon fiber. The price of carbon fiber in the last 1 year, after the Ukraine war started, has gone up sorry, from $10 to $27 per kg. And the availability has come down by 60%, 40%. So the availability is a problem, the price is a problem. And these are driven by geopolitical events, which could be a war somewhere, which could be anything, because just for your information, the same carbon fiber is used for manufacturing missiles. So automatically what happens is the countries demand that the manufacturers of this raw material give focus to their defense industry and not to the commercial industry. Then, of course, there are product development costs. So in this industry, what happens, or what I foresee happening in the next 3 to 5 years is, one, there would be somebody who needs to do the infrastructure development. There is bound to be technology disruption, like, for example, the cryocompressed gas, or let's say somebody like NASA says, there is another technology and we will allow that to be used in the commercial space. So that technology can be used in the market. So I don't know what will happen. And then what I call as policy disruption, which is a combination of various factors. Like today, the United States government, as I know, I think gives a subsidy of $4 per kg of hydrogen, whereas the Indian government gives 50 cents per kg of hydrogen. So why would anybody want to invest in India? They would rather invest in the US. So these are the kind of policy disruptions that a nation can do. Now, technically, these are temporary challenges, but because of the fact that either the Ukraine war or what's happening in Gaza or what we are listening in terms of the rumblings between China and Taiwan, uh, while there has been no actual war, the kind of challenges that India is facing, and so many of these kind of geopolitical events, I at least personally feel that any of these challenges that we see are unlikely to be resolved anytime soon in the next 3 to 5 years. So this journey is going to be harder and longer, requiring deep pockets. Now, this is an opinion by a technology, CEO in Europe. I would leave it to you to read this, but there is a lesson in this opinion where what is happening is he says Europe developed the fuel cell technology in 1838 and 1839. That's how old the technology is. But today, at Toyota and others, it's the Chinese market that drives everything. So the consequences are that Europe, in spite of having the technology for so many years, has not leveraging it and has not leveraged it as compared to China. That's just because of the kind of money that's been poured in. So here, as I said, as a kind of closure to this particular presentation, hydrogen is developing at the same time. Technology and standards are evolving. So one needs to be very, very flexible. The variables in the manufacturing are very many. So this limits the availability and the manufacturing capabilities. The business as usual approach will not work for now. One needs to have innovative support systems from the government as well as industry. And a lot of significant changes in policy would probably be required in order to promote and get this growing faster than what we are currently doing. And this brings me to the last couple of slides, which is the key factor of safety. Like I said, this is the lightest element known to mankind. So when you see even a gasoline or LPG is far more denser as compared to hydrogen or air. And this can very easily escape into the atmosphere. But the problem, it can ignite at very, very low concentrations, which means that if there's an oxygen percentage anywhere between 3 to 75%, it can ignite. Whereas when you take others, they would probably ignite at maybe 15%, 20% concentration of oxygen, which may not be possible in all situations. So the problem with hydrogen, it can ignite at very, very low concentrations. Second, when hydrogen catches fire, you cannot see it by the naked eye. So if you suspect that there is a leak, one must assume that there is a fire and a flame and accordingly react to that particular situation. So with hydrogen, safety becomes the key factor for because of the overall complexity. And as I've written in one of my articles, 80% of the safety is in the interconnecting piping and assemblies and so on, which attracts the lowest focus by any customer because they focus on what costs the maximum, like your compressor or the tank or dispenser or whatever. Whereas those have a very, very low risk of safety, but the maximum safety risk is in the rest of the small 20% cost, and that one needs to focus upon. So when you're trying to look at safety, the important thing before you start a hydrogen project, which is key, is you need to ask, what do you want to protect? Because let us say there is something that is 10 kilometers away. You may feel that even if there's an explosion, I don't need to protect it. But on the other hand, there is something 1 kilometer away and you feel that that is very, very important, then you would need to probably decide that you need to protect that against some untoward incident happening, which means that you want to understand what would be the impact of an explosion over a distance. So before you actually start a project, it is important to do this kind of a study wherein you say, okay, I'm going to have 1000 kgs of hydrogen, 3000 kgs of hydrogen, or whatever. And what happens if there is an explosion? And then accordingly decide what you're going to do. You need to understand what can create an explosion and then work on that basis. Then, as I said, you can create weak spots to direct the explosion. Means that just as water flows, you know, to the lowest point always, you can have a situation where, for example, when you look at on the right side, middle picture, that's a container. Let us say in such a container, you have something inside, but you make the roof of the container so weak that if there's an explosion, the roof goes off so quickly that the entire explosive power goes to the sky, which means that even though there is an impact of the explosion on the sites, on all around, where there could be buildings, where there could be people, the impact would be lesser as compared to if, let us say, all of them were to be designed with equal strength. You have things like, for example, what is called as an ultrasound camera, which even if there's a small leak somewhere in one corner, it can detect it from far and zero in and tell you that, hey, you know what, such and such a place, there's a leak. Because when the hydrogen leaks, it makes a sound that you cannot listen to. So even the slightest leak will make a sound, which can be picked up by this ultrasound camera. Now, these are expensive solutions, but yes, that is one option. Another option is you have infrared cameras which can detect a flame. So which means that what you cannot see with the naked eye, you would be able to see with a camera. And if you suspect a leak, then the camera could tell you whether there is a flame there or not. Now, next is the most cost effective and cheapest option is to have a large number of sensors which could then detect the leak and give you a signal. So you could even have portable leak detectors to go and check. You could have fixed sensors and analyzers. And these are so small that these are not even as small, big as a mobile phone, I would say. So these can be fixed at various locations. And the moment there is any leak, it could detect and give you a signal. Maybe it could light up a red light somewhere or whatever. So that could become your first line of defense and move on to the others depending upon the kind of installation that you're going to be having. So depending upon what you're protecting and how you're protecting, like I said, you could have a roof that is weak, you could have a concrete wall that could reduce impact, and you could have various different kinds of these cameras and sensors. You get a tape that you can wind around every joint where the tape color changes if there's a leak. So you have various different options in running a plant. So to sum up, as I mentioned, with 80% of the risk in the piping, we need to focus on that. And most important is before you start the project, getting a safety and risk analysis done where gas dispersion, explosion, simulations of the fire, they are very important. Now, very often what happens is that a customer thinks, oh, this costs $500,000, it costs $250,000. Now, we can't, invest this kind of money every time. No, you don't have to do that. It is important that you do it once in the beginning for a particular project. Let's say the government of a country can get this study done with a certain assumption, and then the results from that study could give I would probably say more than 80% of the education required when you're designing similar systems elsewhere, which means that this investment on doing the complete safety and risk analysis can be amortized over 5 to 10 projects, where then each project, it would then be probably just 20, $30,000 kind of expense, which is something that's easily affordable. Very often people try to sell you the $500,000 or $300,000 package, and customers assume that I can use it, I'll have to do it for every project, and because of which the focus on this particular safety and risk analysis in the case of hydrogen becomes less. And that is an important thing that one needs to understand. The other thing is that when you do such a study, it can help you to design your overall system and installation, whether it is equipment, buildings, structures, the layout, everything in a way which can reduce your overall cost and actually save the cost that you have spent for this kind of a risk analysis. And last but not the least, most important, I keep telling in the case of hydrogen is, as we speak today in 2024, we don't know what we don't know. And we need to do a significant amount of due diligence to find out what is it that we don't know, so that the risk and the success of our project becomes much higher in terms of the way we execute it. Thank you, everybody.